Okay, thanks. So last time I said almost nothing about braid groups, so I want to, but let me remind you at least what the setup was, largely notation. So last time we talked a little bit about a simply laced Kac-Moody-Weil group. So again, we could talk about more general Coxeter groups, but I'm going to restrict to this case here. So a simply laced Kac-Moody-Weil group has a presentation. This is its Coxeter presentation with finitely many generators, and the relations, well, all the generators have order 2, and then for every pair, you either say that the generators commute or that they braid in the standard 3-term braid relation. So that's a simply laced Kac-Moody-Weil group. And to study this group, one typically studies its action on the root lattice. So the root lattice was, well, if we wanted it to be a lattice, we would be taking the span over the integers, but you could also work with the vector space and take a span over the real numbers or the complex numbers. But the root lattice has a basis given by the simple roots, and it has a pairing on it. And this is the pairing in the basis. And then the point of this is that from the point of view of studying this this group acts linearly on the root lattice. The Weil group acts linearly on the root lattice. This is a formula in terms of the pairing for how the generators act. Okay. Now, just because we'll use it a little bit when we start talking about braid group actions, this is something Juji mentioned in her talk last time. It's convenient to encode basically all of this information into the Dinkin diagram. So this is going to be a graph, a finite graph. So the vertex set is our set S. So you're going to have one vertex for each generator. And now edges, well, we put an edge between I and j when the corresponding generators braid. And we don't put an edge between I and j when the corresponding generators commute. This is just a... So all of this, if you like, is encoded in this graph. If you just have the graph and you take two vertices and you see whether or not they're connected by an edge, that tells you whether or not the generators commute or braid. It also tells you what the pairing between the simple roots is, etc. Okay. And then what I discussed a bit last time is, I think this was originally due to Tietz, is that the action of this abstract group on this root lattice is faithful. And this is the starting point for answering essentially any question one might ask about this abstract group. Yes?
So here you don't have the case where they don't do anything?
Yeah, I'm not, that wouldn't be simply laced.
Okay, yeah.
I did give an example last time which wasn't simply laced, but yeah. Okay, so, and in particular, I gave an example, though I did not really explain it. I gave an example of a non-trivial theorem in group theory about W that you access via this faithful action. So there's this is the theorem of Brink and Howlett. Which says that the language of reduced expressions in W is regular. That is, so again, what does this mean? So here we have a presentation of our group. So the Ri, the Ri are the alphabet, and so a collection of words in this alphabet one might be interested in is the words which are reduced expressions in W. And this theorem is that that language is regular. That is, it's recognized by a finite state automaton. That is, the reduced expressions is recognized by a finite state automaton. So I didn't explain why this theorem is true. I think I did say what this means and worked out an example. So I want to get to braid groups, so I'm not going to say too much more about this, except to advertise it as, I think, a deep and interesting fact about these groups, and also to point out this theorem uses fundamentally this action. So I don't know a proof of this theorem that just proceeds by abstract group theory. In particular, the proof uses the notion of what are called minimal roots. In other words, this is a notion that is defined in L. Okay, so if you like, just take this as advertisement about some interesting structure about Weil groups that's accessible via its action on the root lattice. Also, I bring this up to point out that not everything, of course, not everything is known about these Weil groups. So, for example, a question one can ask, and I think this question was first asked by Castleman, is, so for those of you who think about cells in Coxeter groups and cells in Weil groups, another language one might think about is reduced expressions of elements which lie in a fixed cell, like say a fixed two-sided cell. That's a string of words one might care about. And Castleman asks, and possibly conjectures, or I don't know if he conjectures or asks, whether or not that language is recognized by a finite state automaton. As far as I know, that question is open, even in affine type. So that's an example. I mean, so this sort of structure. So essentially, I mean, how all the questions when asked about a Weil group, you can start asking for cells in Weil groups, and many things are still not known there. Okay.
I have a very simple question.
Yes.
About languages. They seem to only have vocabulary and no grammar.
That's true.
So there's no extra structure that comes from representation theory that can be interpreted in this way?
I mean, I guess I would say that sometimes the extra structure you have, which maybe comes from relations and things like this, tells you what the interesting languages are. But no, I don't, off the top of my head, I don't know an example. I mean, it's an interesting point. I mean, you could imagine enhancing the setup to keep track of some further structure. Okay, other questions? Okay, so now I want to get to braid groups. So the main goal of the talk today is to, let me just remind you where we're headed. So today, we're going to categorify this story. So we're going to consider the action of, I'm going to basically define the action of the braid group on a triangulated category, which categorifies the action of the Weil group on the root lattice. Of course, there's a lot to say in order to define this, so that's basically going to be the whole of today. So this is, again, this is still very much a linear thing. And then, the hope is that these groups, which are not very well understood, can be studied via this action much the same way as W is studied via this action on L. So, so tomorrow I'll try to give you some examples of theorems about these braid groups that one proves using the action. There are plenty of examples to talk about and plenty of interesting things to say. This subject is very much, this kind of question is still, in some sense, very much in its infancy. I think most important work along these lines, at least in this generality, remains to be done. And then Thursday, we're going to relate this linear appearance of the braid group. Acting on a triangulated category. It's a kind of linear appearance of the braid group. It's to its sort of topological appearance, as pi 1 of some sort of hyperplane complement. So this is sort of the sort of thing that comes from geometric group theory and algebraic topology. If you see the braid group defined this way, it's not obvious what it should have to do with linear actions of the braid group. That's the goal of the last thing, and the required language to really make sense of that is again, stability conditions. Okay. Again, that's just a reminder of where we're hopefully headed. Okay, so let's try to categorify the action of the Weil group on the root lattice. In order to do that, actually, it's worth perhaps looking at this equation a little bit. There's a simpler thing you could write down. You could forget about this part and just look at this part. So that's a linear operator one might write down. It looks a little bit silly, but it's worth computing the relations that these operators UI satisfy. So you can check on a sheet of paper if you like, assuming I did it correctly. UI squared is minus 2 UI, and so when the corresponding Weil group generators braid, then this is the relation you get, and when the corresponding Weil group generators commute, so when there's no edge in the Dinkin diagram, then UIUJ and UJUI are both equal to each other, and particularly they're both 0. So some of you will recognize this as the presentation of the temporally Lieb algebra. I mean, there's of course a slight sort of issue here. Typically, if you think about the temporally Lieb algebra in type A as it appears in topology, then this equals 0 you don't see. So, but this definition makes sense for arbitrary W, not just W of type A. I've heard this called the true temporally Lieb algebra of W. That terminology was introduced to me by Ben Elias, so you can blame him if you don't like that. So in other words, this Weil group action on the root lattice is built from this temporally Lieb algebra action on the root lattice. Just in this way, you have you take linear combination of the identity map and this and these UIs. Okay. All right. So armed with that, let's categorify the story. So what do we seek? We seek a category T. What sort of category we'll get to? With an action of the braid group on T by autoequivalences. And again, I'll say more precisely what that means. Okay. Okay. Well, we're doing representation theory, so the categories we like are categories of representations of things, say representations of finite dimensional algebras. So there's a few ways to introduce this definition. I'll do it by defining a finite dimensional algebra and then looking at its module category and studying that. So we need to define a finite dimensional algebra. This algebra, this is known as the zigzag algebra of this is not the only algebra you could introduce. If those of you who think about quiver varieties may know about pre-projective algebras. This whole story could be approached using pre-projective algebras rather than zigzag algebra. Okay, so the zigzag algebra of W. So this algebra is essentially going to be a path algebra. It's going to be a quotient of a path algebra. So we start with our graph gamma. So we start with gamma. Gamma was, whatever graph it was. And now we produce we turn it into a quiver, the doubled quiver of gamma. So every time we have an edge, I double it, and I put one in each orientation. So that's the double quiver. And we define, so the first algebra we consider is the path algebra of this doubled quiver. Okay? So this is the vector space that one considers has a basis given by paths in this quiver, and the multiplication is concatenation of paths. When the paths line up so you can concatenate, that's the definition of the multiplication. When the paths you're multiplying don't line up, then the product is 0. So that's the path algebra, and we're going to, now this path algebra is an infinite dimensional algebra. As long as you've got, as long as your original graph has an edge in it, then you're going to have some loops, so you could have arbitrarily long paths in the path algebra. We want a finite dimensional algebra, so we're going to need to quotient by some ideal, and so what are the relations? So the relations are as follows. So I'm going to kill some linear combinations of paths. The first relation is that any path of length 2 which starts and ends at different vertices is 0. So a path of length 2 that starts and ends at different places we kill. Okay, that's the first kind of relation. Now the the second kind of relation, well, so let's think of, now when we've killed these guys, let's think a little bit about what kind of paths we have left. Well, in particular, let's think about what length 2 paths we have left. The length 2 paths we have left are loops that start and end at the same vertex. So the next relation is that if I have a vertex I, and let's say it's got 2 neighbors j and k, it could have other neighbors, that's okay. So the loop at I that goes through j is the same element in the zigzag algebra as the loop at I that goes through k. So in this path minus this path is 0 in the zigzag algebra. Okay? Slightly annoying. This isn't quite the right definition for very, very small graphs. As long as your graph has as long as gamma has at least 3 vertices, this is the correct definition. If gamma is just a single vertex with no edge, then we'll just define the zigzag algebra to be Cx mod x squared. And if gamma, if the original graph is the Dinkin diagram of SL3, then A gamma is the path algebra of the doubled quiver, and you kill all length 3 paths. So these two cases sort of have to be defined directly. Okay, so that's the zigzag algebra. So if you haven't seen this definition before, then while we're erasing here, I might encourage you to think about why this algebra is finite dimensional as a vector space, and what a basis for it as a vector space might be. So in particular, there's a length 0 path at each vertex. Those guys are perfectly good elements in the zigzag algebra. Each edge defines a length 1 path. And so what we want to think about is what length 2 paths we have left. So I forgot to. Let's see. Okay. So a basis for the zigzag algebra is given by the length 0 paths, which I'll denote by EI. EI is the length 0 path at vertex I. Yes?
So if gamma is not connected, say it's going to give you 2
Oh.
then what?
Yeah. So actually, there's no problem with that definition. It's just that I mean, as always, you can't compose paths on different components. If you like, we should restrict to gamma being connected, but.
No, but if gamma is going to give you just those 2.
Yeah.
Then and you apply the first one, that is infinitely generated. I mean, 2 copies of the same. I mean, just one.
Yeah. So annoying is if let's just say gamma is connected. If gamma is not connected, then then this definition requires that every connected component has at least 2 vertices in it. If there's some connected component that doesn't have 2 vertices in it, then you'll get a sum end of the zigzag algebra, which is just one of these.
So you apply the definition to the connected component, you take the
Yeah.
tensor product.
So but let's just think about gamma being connected. So. And there's no interesting interaction between distinct components. Okay. So a basis, we've got the length 0 paths, EI, 1 for each vertex. We have length 1 paths, so maybe I'll denote xij. That's a path from vertex I to vertex j when there is an edge between them. And now, length 2 paths. Well, what we have left, what length 2 paths do we have left? Well, we have loops at a fixed vertex. And how many loops do we have at a fixed vertex? Well, one of the relations was that we declared that the loop going through J is the same as the loop going through K. So there is, in the quotient, in the zigzag algebra, there's a well-defined loop at vertex I. There's a single loop at vertex I, which you could think of as the loop going through any of the neighbors. So there's the length 2 paths, which I'll call Li. From vertex I to itself. And then that's it. So the point of these relations, this is again an exercise to think about, is a consequence of these relations is that there are no length 3 paths. There are no length 3 paths. So any length 3 path in the path algebra is 0 in the zigzag algebra. So. Okay. Okay. So that's the algebra. So why introduce this algebra? Well, let's. So as a left module over itself, as a left module over itself, the zigzag algebra is a direct sum of these submodules. We're here, so let's introduce, these guys are important, these A gamma EI, which I'll denote here as just P sub I, are indecomposable projective left A gamma modules. As a vector space, what is this module? This is just the span of paths ending at vertex I. So you look at paths ending at vertex I, that's a left module for the zigzag algebra. Okay? One might also be interested in right modules. So if you consider the decomposition of A gamma as a right module, you have the same thing, except you put the idempotence on the left side. So let's let I sub P be the indecomposable projective right A gamma module. Okay. Okay, now here's a computational exercise which should serve to motivate why this algebra is introduced in reference to this problem. So we could, let's compute, or let's do that. The space of A gamma module homomorphisms from Pi to Pj. Which, as a vector space, is actually, so this is, of course, these are left modules. You could also think about right modules, homomorphisms from Pi to Pj, between right modules. Or another vector space which is isomorphic to this, you could think about is you could think about the tensor product of a right module with a left module. So what is this? This is just a vector space. Tensor product of a right module with a left module. And all of these, and what are these? So again, it's going to depend on what I and j are. So we've got the cases to consider I equals j. I and j are distinct but connected by an edge. So the Weil group generators braid, or I and j are distinct and not connected by an edge. Okay, and what does this computation look like? Well, the easiest one to think about is this tensor product. So let's think about what this tensor product is as a vector space. This right module IP is paths which start at vertex I. This left module Pj is paths which end at vertex j. So this tensor product as a vector space has a basis given by paths from I to j modulo the relations we've imposed in the zigzag algebra. So what kind of paths are there from I to j? Well, if I equals j, then what's the dimension of this space? 2. Because there's the length 0 path and there's the loop. So this is when I and j are connected by an edge, how many paths are there from I to j? There's just one, the path from I to j. So. And when I and j are not connected by an edge, there are no paths from I to j, because any path from I to j would have to have length at least 2, and by the relations we've imposed, that kills such a path. Okay.
Can you perhaps recall the argument why this I right is the same as a dual from left?
Sorry, say.
So why all passes to the right? I module why it's a dual to the left one.
Well, this, if you like, this is a hom from here to here. So this is paths ending at I. This is paths ending at j. Any morphism like this is given by taking a path that ends at I and appending to it a path from I to j. So this space also has a basis given by paths from I to j. Here, it's the dual thing. This is path starting at I and this path starting at j. So there's a basis that this path is recomposing. Okay, now one more thing to note. This is important. The path algebra and the zigzag algebra and these modules have a little bit of extra structure. They are graded by path length. I mean, the path algebra is a non-negatively graded algebra where the grading is just given by the length of a path. And the relations we have imposed are homogeneous for path length. So the grading on the path algebra descends to a grading on the zigzag algebra. And these modules also inherit a grading. So, so let's write down the graded dimension. So let's look at this computation and let's write down the graded dimension of any of these spaces. So it's 1 plus q squared for q for 0. So in particular, if you think about taking q to minus 1, you see the pairing between simple roots in the root lattice. So the pairing between simple roots in the root lattice, which is, these are some numbers, have been upgraded to vector spaces. So this is a, so if you like, you could say that, so this is one way to make precise the statement that the category of modules over the zigzag algebra categorifies the root lattice. So let's say that a little more precisely. Okay, so let me state that a little bit more precisely. So a category that one might be interested in, so let's let C be the category whose objects are graded projective left modules over the zigzag algebra. And whose morphisms are left module morphisms which preserve the grading. So the objects of C are finite direct sums of shifts of these indecomposable projective modules. So you can take direct sums and grading shifts of these modules. And the morphisms are just the morphisms of graded modules. So then what we've said is that the Grothendieck group of this category, after setting the shift value to -1, is isomorphic to the root lattice. And the isomorphism takes the class of the indecomposable projective module Pi to the simple root alpha I. The pairing over here is just the graded dimension of Helm spaces here, with the grading then set to -1. So this is this is a version of the statement that this C categorifies L. Okay, now that by itself is not that interesting, because this is just a free abelian group with a pairing on it. What's interesting here is the fact that it has this temporally Lieb algebra action, Weil group action. The symmetry here is what's interesting. So in order to justify the study of this guy, we should ask ourselves what sort of symmetry this category has. So ideally, C would have interesting symmetry related to the action of W on L. Okay. Start with a kind of positive statement. So well, C is a category of modules. If you want a functor from the category of modules to the category of modules, there's basically one source of functors from module categories to module categories, and that's bimodules, tensoring with bimodules. So the natural place to look for any sort of symmetry is to look for some bimodules. So here's some bimodules you can write down. So let's define UI. So UI is going to be the tensor product of a left module with a right module over the ground, right? And just for pleasantness, I'm going to shift the grading down by 1. Okay, so this UI is a graded projective, but that maybe doesn't matter for now, is a graded bimodule over the zigzag algebra. Okay? Now, the computational exercise I erased told you how to tensor right modules and left modules. So that computation is enough to figure out what happens when you start tensoring these bimodules together. So this is an exercise which follows from the computation of Helms we did earlier. So if we take the bimodule, what relations hold between these bimodules? Well, this is isomorphic to sum of two copies of the bimodule UI. And if the generators, if the I and J are connected in the Dinkin diagram, and if I and J are distinct but not connected in the Dinkin diagram, so the bimodules UI satisfy categorical versions of the temporally Lieb algebra relations. So this is so the UI give a categorification of this of the temporally Lieb algebra associated to W. Again, if you're used to the type A temporally Lieb algebra, you typically wouldn't have this. So not homology is not the direction that we're going in these lectures, but just as an aside for the Kovanov homology people. Of course, we could look at the zigzag algebra in type A, and then this really would be a quotient of the temporally Lieb algebra in type A by this. So you could ask if you can get link invariance from this, and yes, you can. But this fact, the fact that you get 0 here, essentially tells you that you don't get a very interesting link invariant. The tangle invariants here just collapse too quickly. So this is not as so if you study Kovanov's arc algebras and their cousins, then you still get relations like this for bimodules, but you don't have a 0 here, and you get a more interesting link invariant. So you do get link invariants directly from this picture, but by themselves, they're not particularly interesting topological invariants. Okay. So that's a sense, at least, in which C has some structure that looks a little bit like the root lattice. So now here's so the next question we might ask. So what about the more interesting thing? So what about something like the Weil group action on L? Which remember was so this is the formula for the Weil group action. Does this lift to some group action on C? I mean, this part we lifted to a temporally Lieb algebra action. Now, most of the time, I think when one first sees this kind of question, I mean, the answer you usually you see is no, and at least the justification I first heard for why the answer is no is because this minus sign doesn't make sense in the category C. That's true, but that's not really why you can't do that. There's a better conceptual explanation for why the answer is no, and that's because categories like C cannot have interesting group actions on them. So C, what kind of category is C? C was projective modules over a finite dimensional algebra. So C is an additive category. So the structure in C, you can take direct sums of objects, and every object is isomorphic to a direct sum of indecomposable objects. So in such categories, you cannot have interesting group actions, at least not by additive functors. So why? So let's say that you have a functor from C to C, an additive functor, meaning that f of A direct sum B is f of A direct sum f of B. And let's say this functor is invertible. Let's say it's an equivalence. Of course, if you have group actions, then this would have to be an equivalence. Then, what is f of pi? What are the possible outputs for f of pi? Now I ask you this. So this is an indecomposable object in the category. So it has to be indecomposable. So there's just not that much, there's just nowhere interesting to send this. This has to be some shift of some indecomposable, it's got to be something like this. In other words, up to grading shifts, this functor just has to permute the indecomposable objects. This is akin to if you were studying, learning about vector spaces and you always wanted to work in a fixed basis, and then the only linear transformations you might ask about is you could say, well, look, is there an invertible linear transformation which actually fixes this basis as a set? Well, that's not a very interesting group action, it's just a permutation action, okay? So categories like this, or abelian categories, the same sort of argument applies, basically they can't have very interesting group actions on them, other than things which permute the simple objects or the indecomposable objects or something like that. So there's no hope of getting, of course, if you look at the Weil group action here, the Weil group action here does not preserve the simple roots. So, so if you want to study group actions on categories like this, you are forced to leave the world of abelian categories and additive categories. Of course, now, those of you who've seen link homology and things like this know that what you're supposed to do here is pass to complexes. So that's what we're going to do. But this fact, so the fact that additive or maybe abelian categories don't have many interesting group actions on them, forces us to move to triangulated, or maybe DG, or maybe A infinity categories. So if you want to know why people who study categorical group actions talk about triangulated categories, it's not necessarily because we love the abstraction of triangulated categories and the octahedral axiom and all that sort of stuff. It's because we like groups. So, so that's the reason. Yes?
How strong is the force?
How strong is the force? Well, I mean, that's a fair question, and I've stated this vague enough that I think I can give you a kind of a vague answer. So, for example, let's say you were talking about abelian categories, unless your abelian category were coherent sheaves on an algebraic variety. Then you could ask, what are the exact autoequivalences of that category? And they're exactly the automorphisms of the variety. So the abelian category of sheaves doesn't see any symmetry that the variety already didn't see. But the derived category, of course, has many more interesting ones. So, I mean, so in particular, force here means if you don't want the action to just permute the set of simple objects, then you at least have to move to triangulated categories. I don't know how many other formalisms there are that might have some interesting group representation theory, but this is what seems to show up in nature. So, yeah. Okay. Okay. So I better. So what do we do? So if we want to look for an interesting group action, we can't act on C. Yes.
Just a stupid question. What if you look for functors that are not additive?
Say again?
What if you look for functors that are not additive?
That are not additive. Then I have no idea what to say in general. That's like looking at endomorphisms of a vector space that aren't linear. I mean, you have to say something about what structure it preserves, I think, to say anything with content. But so, right, so what was okay. So, okay, so, what are we going to replace C with? Okay, so first let's look at, chain complexes in C. So the objects here are chain complexes. Or the chain groups are objects of C. So you can put together objects of C into, say again? Sure, yeah. I mean, you can take bounded, you don't have to take bounded. So, and morphisms are just chain maps. Okay. Now, if C were in a abelian category, for example, then this category would still be abelian. So again, this category is not a very natural place to look for group actions. But so now now the next step is this is the homotopy category. So what do we do in the homotopy category? The homotopy category has the same objects, just chain complexes, but we change the morphisms. So we just kill all the null homotopic chain maps. So hom and hom C from A to B is chain maps and you just kill all the null homotopic chain maps. This category, this category, of course, if C were additive, this category is still additive, and this category is still additive. But if C were abelian, this category would be abelian. This category is no longer abelian. You can't take the kernel of a morphism here. You can take the kernel of a chain map, but if you change that chain map by a null homotopic chain map, the kernel over here might change. So kernel doesn't immediately make sense. The kernel of a morphism here doesn't quite make sense. So this category C is not, even if C is abelian, this category won't be abelian. But whenever C is an additive category, this category is triangulated. Okay. So what sort of structure does that involve? Basically, two important points. The first is that if you have an object in the homotopy category, you can shift it. And here I don't mean internal grading shift, I mean homological shift. So of C. One is you can homological shift. So I can take a complex and I can just shift the chain complex. And you can take the cone of a morphism. So the cone of a morphism, let's say I have a map F from M to N. Then I can form a new object called the cone. By the chain group is just the direct sum of the chain groups of M and the shift of the chain groups of M and the chain groups of N. And the differential is just drawn like this. It's the differential in M, the differential in N, and you put the chain map F to move between M and N. So this is a way to take a morphism between two objects and produce a new object. So that's part of the structure that this triangulated category has. Okay. So now back to our situation with zigzag algebras. So let's look at the bimodule UI with the internal grading shifted up by 1. So this was okay. Then because UI had the grading shifted down, so I shifted it back up. Now this is an AA bimodule. Now there is a map of AA bimodules. There's a natural map of AA bimodules from this guy to the zigzag algebra itself as an AA bimodule. So what is that map? So remember, this PI here was paths which end at I. This was paths which start at I. This is all paths. So this is a path which ends at I, tensor path which starts at I, and this is all paths. There's a natural map. Just concatenate the paths. Multiplication in the algebra. So this gives us a chain complex of bimodules. Okay, which I'm going to call sigma I. And these are the things which will give our braid group action. Okay? So I'll say more about that. I'll spell that out in detail at the beginning of tomorrow's talk. But the upshot here is this is very much like the, so these guys were temporally Lieb. And this tensoring with A gamma is the identity functor. And so we've taken something like the identity minus the temporally Lieb guy, which was the formula for getting the Weil group action from the temporally Lieb algebra action. So, okay, but we'll pause there and we'll continue.
In that case, the A gamma to categorize A gamma module, this one is not having
Right. Right. Just additive. But the homotopic category is still triangulated.
But then